let's build a neural network. Okay, go to collab.research.google.com, click on the new notebook option. We're going to use Collab's California housing data. So if you click on the left side where the files are, it'll connect to a runtime, and then you should see sample data. Open that up and go ahead and copy the path to the California housing train data. So you do that, the three dots, hit copy path, and then I'll call this data train. Okay, set an equal sign, and then in quotes, put that path in there, Command V. And then we've also got a separate testing data, so we don't have to split it. And inside of quotes, come back to your sidebar, find the California housing test data, click on the three dots, copy the path, put it in there, and then we will go ahead and open these up. So after you do that, you can close out your side window, and then do the import pandas as PD, and df equals pd.read_csv data train. And I'll also go ahead and do the df test, and that's pd.read_csv data test. And then let's go ahead and look at the test data with the df head. Okay, let's go ahead and press Shift Enter to do that. This is the California housing data, and we're just going to move through this quickly. We have data on groups of houses, and it's common to try to predict the median house value, and that was what we were going to do using a neural network. So, what's the first thing we need to do? Well, we need to separate out the y value, which is the median house value. So y equals df, I'm just going to go with last, df.iloc, I'll take all the rows and the last column, and then capital X, we're going to use df.iloc, all the rows, and going all the way up to but excluding the last column. Okay, so now we've established our X and our Y, and we are going to be ready to build a neural network. Okay, so I will call this intro neural nets. And sometimes I like to put the data set in here, so I'm going to put California housing. All right, so how do we turn this into a neural network? We are going to use the keras library. Keras is a high-level version of TensorFlow, which is Google. It's used by a lot of companies and researchers in the world today. So what we need is the sequential model. Sequence means, in effect, you're going from left to right, kind of like that picture with the neural networks. So it's from keras.models, and then you're going to import sequential. And then the other piece that's very common, in addition to the left to right, is the it's the dense, when they're densely connected, meaning each node connects to every other. So also try from keras.layers import dense. It should be enough. Okay. So now we're ready to kind of build the neural network. And the first thing we're going to do, I'll put the steps in, is initialize model. Okay, it's a sequential model. So as you might expect, we set model equal to sequential with parentheses. Okay, now what? Now this is where it gets fun. Okay, we are going to add a hidden layer, right? So we have all these columns of data, and we're going to direct them all to a new sort of, when I say columns, but it's not really columns, it's like, it's a layer, and a layer is a series of nodes, and we're going to pick the number of nodes. Okay, and so the way you do this, we have a model, you do model.add. Now, we're going to add a dense layer, meaning everything connects to everything else. And so you put the dense in and then a parentheses. Okay, so we've got parentheses inside of parentheses. And then what we need to put are the number of nodes here. And I wouldn't go too crazy, meaning like not too big, because obviously the more nodes you pick, the more weights it's going to have to find. I don't know. I will try keep it simple, like something like 8. And then in this first one, okay, this first hidden layer, the 8th is telling you sort of, you could think, okay, you're going to find 8 new weights per like whatever's coming next, but it needs to know how many weights are coming in. And so you do that by setting the input shape. Okay, now the input shape is the number of columns. Okay, and so how can we specify the number of columns? Okay, there are different ways to do this. I'll just add it in here, get number of columns. Okay, well, if we call this like num calls, then we would set this equal to, well, we've got x dot shape. Shape gives you rows, columns, and it's 1 is the number of columns. Okay, and so when you do that now, in effect, you can put in here number of columns, and you just put a comma after that to allow it to get the right number of rows. Now you go outside of that parenthesis. Wait a minute. Input shape should have its own parentheses. Okay. You got a lot of parentheses. One of the most common errors when people first start doing this is how to specify the parentheses. So after the input shape, we want another feature of our dense layer, and that's what makes it nonlinear, and that's the activation function. And so for activation, I'm going to go with ReLU. And so go ahead and do the same ReLU. You could always try something different like tan H if you want to do the tangent inverse function. Okay, so this is now a hidden layer. It's set to connect to all the columns. Okay, and then for kind of a relatively simple neural net, we're just going to go ahead and add the output layer. Okay, so we're going to add an output layer. And this is what we're trying to predict, right? So now if you think about what the output layer should be, okay, what do we need to do here? Okay, well, we gotta have an idea of what we're trying to predict. So recall, we're trying to predict these median house values. These could be any number, so it's regression. And so again, think back to the visual of the slides. In effect, you want an output layer of, well, we want it densely connected to the previous layer, and you want it to be 1. You want one node only. It has to be 1. Okay, that's the key. And you could or could not have an activation function here. What's sort of interesting because it's, if ReLU maps to positives, it maps all negatives to 0. Median house value is going to be positive. So, you could or could not add, you could add a ReLU here, which, I think it kind of makes sense. I'm going to go ahead and add it, because it forces everything to be positive. We don't want any negative house values. And then something we can do now, okay, so what we've done here, let's keep this as our neural network. We have one hidden layer with 8 nodes and then going straight to an output. This is a neural network. And what we can get is a model summary. This is before we actually connect it with our data. So you can print out model.summary. I think this is always a nice idea. So let's run this code and see what we get. Okay, what's nice about this is we get the total number of parameters. It's only 81, so it's not a lot. And it's showing sequential model, do not pass input shape. Okay, sometimes they change things over time. We'll look at some of that later. But it looks fine. It's just not, I do this because it's nice to see your total number of parameters. Okay. And this was suggest 9 times 8 is 72, and then you're going to add 8 more and you have a final output. Okay, so this looks good. And what we're going to do next is compile the model. Okay, so that's sort of like what we've basically done here. Kind of like before, it's like, hey, we're going to use linear regression. This is the model that we're going to use. But what's cool is you, as the programmer, play a role in building it because you're kind of picking the hidden layer along with these activation functions. And so now we're going to compile the model, okay? And so to compile the model, we go to model dot, you could guess, what do you think it is if we're going to compile it? Compile, it's right there. And what we can choose here is the optimizer. And the optimizer is like, what kind of calculus are we going to use for backpropagation, atom, and for the loss function, it's MSE. Okay, So, and then we can fit the model to our data. Right now, this is not sklearn, so it uses a different kind of a syntax. And what we're going to do model.fit, and we're going to fit it on x comma y. Now, you get to pick the number of times it's going to go back and update the weights. And that's the number of epochs. And I'll try to start with a reasonably small number, like 20. Okay. And then I think from here, you know, what we can do, let's just go ahead and do this right. I think that's the minimum we need. And then let's go ahead and score the model. Okay. And so we score it really on the test set. All right. And so how do we do that? Well, we didn't actually establish the text set, but if we go back up here, you know, we add in a Y test and an X test. And then instead of using df, of course, we use df test. Everything else is the same. And so just put in your .ilog, -1 for y, and df test.ilog, and then all the way up to, but excluding -1 for x test. Okay, now you put that code in there, it has not run. You got to run it again to get it to work. So I'll go ahead and run that code again. With the advantage being, again, let me just hold that. Sorry, I don't want to go too quickly for you all. Added just a y test and an x test. Pause if you need to get that in there and run it again. And then go all the way down. And then when you score the model, okay, we're going to use the RMSE. So it's going to give the MSE, and for that we're going to do model.evaluate on the X test and the Y test. So basically we build it, but we want to see, okay, how does it do on the X test and Y test? And then we can compute the root mean squared error from that, which is just the mean squared error to the 0.5, because the square root. And that's what we print as the RMSE. And recall that what the root mean squared error is it gives you the number off that you are from the housing predictions. So it's a good idea to have kind of what we're looking for here. Okay, so 700,000, right? These are in the hundreds of thousands on average. And so, you know, if we got a root mean squared error of like 200,000, that means our predictions would be 200,000 off on average. Okay, so hopefully you've got this. And what's cool now is the model should run if we don't have any errors, and we should see it sort of running. Okay, so let's go ahead and press Shift-Enter and watch it in action, and then I'll talk a little bit about what it's doing as we look at it. Okay, good, it is working. So basically, it's showing the mean squared error, okay? And what we're looking here as it's running through the epochs is that it is going down. Okay, the loss is going down, indicating that learning is taking place, right? Whenever your loss goes down, it's learning. You can see it's starting to like not learn as much. It's getting a little bit stalled out around 26, 25,000, but it is still getting better. Now I only gave it 20 epochs, so it's going to stop here. And at the very end, it prints out the root mean squared error, which is about 150,000. Okay, so that is deep learning in action.